Hi. Today we're going to build a matrix called the Jacobian, which is going to help us with change of variables when we're computing either double or triple integrals. So let's just remember how the story starts. You can have a plane, a UV plane like this, and maybe you have some really nice region like the following, which is rectangular. And we like rectangular regions because it's very easy to describe what these look like using double integrals. So you're going to have, like, say we had a double integral here, you'd have a double integral and it would be like, say, from A to B here, and maybe this is C to D, so A to B, C to D, and those are really nice limits of integration. So that might be a reason why we would do this. Okay, so we're going to get rid of all that, and we're going to remember how this story starts. Okay, and there's a second plane, the XY plane, and maybe in the XY plane, you've got a region which, for some reason, the way it's described just doesn't look as nice. Maybe this is it. This is going to be the region R. Okay. And what we've investigated in prior videos is that it's a transformation that takes you from the UV plane to the XY plane. And often the shapes we get in that XY plane don't look so good. Okay, so let's just do a little bit of notation. Let's say, for example, that we're going to call this side v equals v0. v0 is a constant number, and so this side of the little rectangle would be v equals some kind of number. Okay, and then similarly, maybe this side we would call u equals u0. And then right here in the corner, I'll use a different color, maybe that's the point u0 comma v0. Well, after applying the transformation, u0 v0 gets mapped over to this location, which we're going to call x0 comma y0. So what we can say is, for example, we can say the transformation t applied to the point u0 v0 gives you the point x0 y0. And if you look at the other videos that precede this, there's nice examples of that. And then similarly, this side is what happens when we take the bottom side of S over in the UV plane and map it over to here. A good name for that, I'm going to call this R of U comma V0. And you might say, why R? R is just a vector function, and it takes takes U and V and does something to them. You'll notice that U here is free to span a bunch of values, but V0 is fixed. And then the same reasoning tells us that a good thing to call this would be R, lowercase r, sorry, of u0 comma v. So that's the theory. That's what we're really doing. And what we're saying is that this function R of u comma v does the following. It does something to u and v to get the x component of the resulting vector, and it does something else to the u and v to get the j component or the y component of that thing. Okay, so what we can do now if we want is we can compute the following. I'm interested in two vectors. We can find a vector that does this. So we're up here in this plane, goes out like that. I'm going to call that vector r of u. That represents the tangent vector to this region at the point x0, y0. And similarly, we could find this vector. We'll call that r sub v, which is the tangent vector to the region at the point x0, y0 in the v direction. Okay, so how can we denote these things? That's where things get a little bit wild, but we'll give it a shot here. We could say, actually, let's color code it. Would you use red there? All right, so we'll say that r of u equals g sub u of u comma v times I plus h sub u of u comma v times j. Now g sub u, for example, and h sub u mean the partial derivative of the function with respect to u. If we want, we could also denote this as partial x partial u times I plus partial y times partial u times j. Okay, so what this crazy thing is, looks crazy to look at, it's really just this tangent vector over here, up here in this corner. It's this tangent vector we're looking at. Okay, so now I want to go find this purple tangent vector, r sub v. So right up there, we want to look at r sub v, and how do we do that? Well, surprisingly similar to what we just did. R sub v equals g sub v of u comma v times I plus h sub v of u comma v times j. Or if we want, we can write partial x partial v times I plus partial y partial v times j. Again, we're finding partial with respect to v in this case. Okay, so what's next? Well, I want to go back to this region R again. So we're going to focus a lot on this picture. I'm going to redraw it on the next page. Okay, so that was quick, but I spared you watching me draw that over again because that took a while. All right, so what I'm going to do is I'm going to look at this picture in the upper right here, and we called this vector r sub u, but if I wanted to estimate the length of this side using this vector, what I could say, well, it's r sub u times some delta u, some small change in u, that this would be sort of like a distance, and this is like a direction, so if I multiply, it gives me the length of that side. And in the same sense, this was r sub v, so we did delta v times r sub v, we would again have like a distance times a vector, gives us a direction, gives us the length of that little side there. Okay, so there's another thing we could do also if we want to estimate those sides. So we're gonna go over this picture here, and you notice I'm erasing those tangent vectors. And what I'm going to draw in instead, let's use a more dramatic color, I'm going to draw in these two vectors, these little green vectors, and these are secant vectors. So for example, this secant vector on the bottom, we can call r of u sub 0 plus delta u, comma v0. Now, it might be a little confusing where that's coming from, but let's go back to the original picture. If we look at this literal rectangle up here, this one, then what I'm really suggesting is that the length of the base is delta u, and the length, or how tall it is delta v. So then that makes, if we go over to the picture on the right here, this point here, out here, is the point r of u0 plus delta u. That's what that is, comma v0. So that's what's happening, and that's what I'm getting here. Okay, and so I should really be more careful. This little arrow is not quite right. What this is this point in the corner. So this gives us that point right there. This point over here is the point r of u0 comma v0. And in the same spirit, this is the point r of u0 comma v0 plus delta v. Okay, so here's where the fun part is. We can find those two secant vectors. So let's give them names. I'm going to call this secant vector number 1 and this secant vector number 2. So secant vector number 1 is just r of u0 plus delta u comma v0. And we're going to subtract off the starting vector, which is r of u0 comma v0. Vector 2 is going to be r of u0 comma, I'm going for this one up here, minus that one. So r of u0 comma v0 plus delta v minus r of u0 v0. Okay, so here comes something fun. Consider this definition of the partial derivative. R sub u is the limit as delta u goes to 0 of r of u0 plus delta u comma v0 minus r of u0 comma v0 all over delta u. So what does this tell us? Well, it tells us that delta u times r sub u is approximately equal to the numerator of that difference quotient, this thing, delta u comma v0 minus r of u0 comma v0. And that's sort of interesting because if you think about the picture up above, that's sort of telling us that, let's use a dramatic color here, that this vector here and this vector here are approximately the same. And then similar reasoning will tell you that this vector and this vector are approximately the same. We can write that if we want the way we wrote the other one. We can say that delta v r sub v is approximately r of u0 comma v0 plus delta v minus r of u0 comma v0. Okay, but what we also showed in an earlier video was this proof about the norm of a cross product. So it turns out that if we want the area of this region R, which is ultimately what we want, the area of R, that's equal to the norm of the cross product of these two things. So that's what you have here. This thing cross this thing. So that's actually really nice. Now there's a property of cross products that I have not proven to you, but you can look up a proof of it. These two things are really scalar quantities. They can be factored out. So the final expression that you get is r sub u cross r sub v times delta u delta v. Oops, let's just fix that. I'm thinking ahead to the integral there. You can kind of see it. And it turns out that this thing here has a special name. That thing is called the Jacobian. And you know just by looking at it that it's going to be a scalar quantity because it's the length of a cross product of a vector. And therefore, it is giving you, in a sense, the ratio of the areas of the region S over here to the region R over here. So that's what that Jacobian does. And in many ways, this is a more generalized version of what you do when you do U substitutions. You do integrals of a single variable. You end up with this constant you have to multiply by, which really becomes the scalar that you have to multiply your original area by, or your original, and that's exactly what's happening here. So in the next video, we'll do a computation. Okay, I guess one last thing we could do just in terms of notation, you can write this as a determinant if you like. You can write I, J, K, that's how we write cross products. And then it's, since it says R sub U, we showed already R sub U is really this thing. So that'll be the first row of our Jacobian matrix. And then this thing will be the second row of our Jacobian matrix. So here we go. Get ready. So we'll write that out. This we can write as partial x partial u, comma partial y partial u, and then 0, because these vectors are just in the 2D plane for now. And then you're going to have partial x partial v, and then partial y partial v. So that's it. And this gives you the constant by which you have to multiply. If you take the time to actually compute this, which I will spare you, here's what you end up with. You end up with, if you remember how to do determinants, you'll end up with this expression. Partial x partial u, partial x partial v, partial y partial u, partial y partial v. And there you go. There you have it. Thanks for watching.